Radioactive decay is a constant quiet force in the universe. It is the process by which unstable atomic nuclei lose energy. They do this by emitting radiation. This might sound like a small thing, a detail of physics, but this process is fundamental to the cosmos as we know it. It shapes stars, heats planets, and even allows us to date the past. Imagine for a moment if this fundamental process just stopped. What if all the atoms in the universe that were prone to decay suddenly became stable? The universe would be a profoundly different place, almost alien to our current understanding and experience. The universe is always changing. Stars are born, they live and they die. Planets form and evolve over billions of years. Life itself is a story of continuous transformation. Radioactive decay is a key player in many of these grand cosmic narratives. It is an unseen engine, tirelessly working, driving change from the smallest scales of atomic nuclei to the largest scales of galactic evolution. It is a subtle whisper of transformation that echoes through all of space and time. Without this constant, spontaneous change at the heart of matter, the story of the universe would be unrecognizably altered in its most basic chapters. Consider the very air you breathe, the ground beneath your feet. Much of what constitutes our world has been influenced directly or indirectly by radioactive decay. The heat within our Earth driving geological activity is largely a product of this decay. The ability to understand the vast timescales of our planet's history relies on it. Even some of the elements that make up our world and our bodies have origins tied to the life cycles of stars, where decay processes play their part. To stop radioactive decay would be to pull a crucial thread from the intricate tapestry of existence, with consequences unraveling everywhere. So let us embark on a thought experiment. We will explore a hypothetical universe where one day radioactive decay simply ceases. No more atoms splitting apart spontaneously. No more release of energetic particles from unstable nuclei. What would this silent universe look like? How would the absence of this fundamental process reshape our understanding of physics, geology, biology, and our place in the cosmos? It is a journey into a quieter, perhaps more static, but certainly an astonishingly different reality than the one we inhabit today, a reality we take for granted. At the core of every atom lies a nucleus. This nucleus is made of protons and neutrons. Protons have a positive electric charge. Neutrons have no charge. The number of protons defines what element an atom is. For example, an atom with 1 proton is hydrogen. An atom with 6 protons is carbon. These are fundamental building blocks of everything we see and are. However, not all combinations of protons and neutrons within a nucleus are stable indefinitely. Some nuclei are inherently restless, holding too much energy. This restlessness is the origin of radioactivity. Some atomic nuclei have too many neutrons or too few. This imbalance makes them unstable. Think of it like a tower built with uneven blocks. It wants to settle into a more stable shape. Unstable nuclei try to reach a more stable, lower energy state. To do this, they spontaneously release energy. This energy can be in the form of particles, like alpha particles or beta particles, or it can be in the form of high-energy photons, called gamma rays. This entire process is what we call radioactive decay. When a nucleus decays, it often transforms into a different nucleus. It might change the number of its protons or neutrons. This means the atom can change from one element into another. For instance, radioactive carbon-14 with 6 protons and 8 neutrons decays into nitrogen-14, which has 7 protons and 7 neutrons. This transmutation of elements is a natural alchemy driven by the laws of physics. It is a fundamental way that matter reorganizes itself, seeking equilibrium. This process happens at a predictable rate for each type of unstable atom, a rate we call its half-life. So radioactivity is not some mysterious, artificial force. It is a natural property of certain types of matter. It is the universe's way of ensuring that atomic arrangements find their most comfortable configurations. This release of energy and transformation of elements has profound consequences, as we will see. It is a constant background hum in the symphony of the cosmos. A hum that, if silenced, would lead to a dramatically altered composition, leaving the universe in a state of suspended atomic animation, with many elements frozen in their unstable forms. Imagine a universe where this fundamental process of radioactive decay suddenly halts. All those restless atomic nuclei, poised to transform, would simply stay as they are. Uranium would remain uranium, never turning into lead. Carbon-14 would remain carbon-14, never becoming nitrogen. The periodic table of elements, as we know it, would become a static catalogue. Those elements we currently identify as radioactive would persist indefinitely in their unstable forms, a silent testament to a process that no longer operates. This would be a universe frozen at the atomic level. The immediate consequence is that the natural transmutation of elements on Earth and throughout the cosmos where decay occurs would cease. Elements that are products of decay chains would no longer be naturally replenished. For example, radon gas, which seeps from the ground, is a product of uranium decay. In this new, silent universe, the existing radon would eventually dissipate and no new radon would form. The Earth's elemental composition, slowly shifting over eons, would lock into place. This atomic stillness would have far-reaching implications for the chemical and physical nature of planets and stars. Furthermore, the energy released by radioactive decay would vanish. This energy, though often subtle, contributes to the heat budget of celestial bodies. It warms the interiors of planets like Earth. It can influence the behavior of materials in interstellar space. Without this constant, slow release of energy, a gentle warmth would be extinguished from many corners of the cosmos. The universe would become a slightly colder, less dynamic place. This lack of decay energy would not just be a minor temperature adjustment, it would fundamentally alter geological and atmospheric processes on a planetary scale. The very definition of some elements would change. Elements like technetium and promethium have no stable isotopes. They exist naturally on Earth only because they are continually produced by the decay of other elements or through spontaneous fission. If decay stopped, and if they weren't being produced by other means, like in specific stellar environments, their presence would be solely reliant on their initial creation in stars. Over time, any existing samples of these elements, if they were still undergoing some other form of slow transformation not classified as typical decay, might behave differently or simply persist as relics of a bygone era of atomic restlessness. Stars are the great cosmic forges. Deep within their fiery hearts, nuclear fusion creates lighter elements from hydrogen and helium. This process builds up the elements like carbon, oxygen, and iron. These are the building blocks of planets and life. When massive stars reach the end of their lives, they explode as supernovae. These colossal explosions scatter newly forged elements across space. This stardust then becomes the raw material for new stars, new planets, and perhaps new life. It is a magnificent cycle of cosmic creation and recycling. Radioactive decay plays a role in this stellar alchemy, particularly in the aftermath of supernovae. The intense conditions during a supernova can create many heavy, unstable nuclei. As these unstable nuclei decay, they can transform into other elements, contributing to the rich diversity of the periodic table. Some specific isotopes, or even entire elements heavier than iron, are thought to be significantly produced through rapid neutron capture, followed by beta decay, the R process. If radioactive decay never existed or stopped, the final elemental abundances produced by stars and supernova would be different. The universe would be poorer in certain heavy elements, considered the elements heavier than lead and bismuth. Many of these are radioactive. Their existence and relative abundances in the cosmos are tied to decay chains and the stability of their various isotopes. If decay pathways were absent, the chain of creation might stop prematurely for some elements. The universe's elemental composition would be skewed towards lighter elements or different isotopic ratios. The glorious spectrum of materials that make up our universe would be less varied. The specific mix of ingredients available for planet formation would be altered, potentially impacting the types of worlds that could form. Moreover, the light curves of supernovae, the way their brightness changes over time after the explosion, are powered in part by the radioactive decay of elements like nickel-56 and cobalt-56. This radioactive glow allows astronomers to study these distant explosions in detail. If this decay stopped, supernovae would appear different. They might fade much faster, or their light signatures would lack these characteristic features. Our understanding of these cataclysmic events and the element creation they trigger would be less complete. The cosmic fireworks would lose some of their most informative sparks. Section 5, Earth's inner chill, a planet without its radioactive warmth. Our planet Earth is not a cold, dead rock. It has a warm interior. This internal heat comes from two main sources. One is the leftover heat from its formation billions of years ago. The other, and very significant source, is the radioactive decay of certain elements within the Earth's crust and mantle. Elements like uranium, thorium, and potassium have unstable isotopes. As these isotopes decay over geological timescales, they release a steady stream of heat. This heat is crucial for our planet's dynamism. If this radioactive decay suddenly stopped, this vital internal heat source would be switched off. The Earth would begin to cool down much faster than it is currently. While the residual heat from formation would still exist, the ongoing replenishment of heat from decay would cease. Over millions of years, the Earth's interior would become significantly colder. This cooling would not just be a minor temperature drop. It would have profound and cascading effects on the geological processes that shape our world, turning our dynamic planet into something far more static and frigid from within. Geothermal energy, which we harness in some regions for power, is a direct result of this internal heat. Hot springs, geysers, and volcanic activity are all surface manifestations of the immense heat stored within the Earth. If radioactive decay stopped, these geothermal phenomena would gradually diminish and eventually disappear. The planet's internal furnace would no longer be stoked by atomic transformations. This would mean a loss of a renewable energy source for us, but more fundamentally, it signals a deep change in the planet's thermal state and its ability to drive geological activity. The consequences of a colder interior would extend deep into the planet's structure. The mantle, the thick layer between the crust and the core, behaves like a very viscous fluid over long timescales. Its convection currents, driven by heat, are responsible for moving the tectonic plates. If the heat from radioactive decay vanished, these convection currents would slow down and eventually stop. The engine driving plate tectonics would sputter and die. This would lead to a geologically quiescent Earth, a stark contrast to the active evolving planet we inhabit today. Section 6. A geologically static world, tectonics halted, shield down. The Earth's surface is constantly being reshaped. Mountains rise, continents drift, and oceans open and close. This dynamic activity is known as plate tectonics. It is driven by the convection currents in the mantle, which are in turn significantly powered by the heat from radioactive decay. If this decay stopped and the Earth's interior cooled, plate tectonics would grind to a halt. The continents would cease their slow dance across the globe. Mountain building driven by colliding plates would largely end. Volcanic eruptions and earthquakes common at plate boundaries would become exceedingly rare. Without plate tectonics, the rock cycle would be severely disrupted. This cycle involves the creation of new rocks, their erosion, and their transformation. Tectonics plays a crucial role in recycling crustal material back into the mantle and bringing new material to the surface through volcanism. A geologically dead Earth would mean that erosion would gradually wear down mountains, but there would be no new mountain ranges forming. The landscape would become flatter, older, and less diverse over geological time. The vibrant geological youthfulness of our planet would fade into a monotonous old age. Furthermore, Earth's internal heat and the convection in its liquid outer core are essential for generating our planet's magnetic field. This magnetic field acts like a shield. It protects us from harmful solar wind and cosmic radiation. It deflects charged particles from the sun, preventing them from stripping away our atmosphere and bombarding life on the surface. If the Earth's interior cooled significantly due to the cessation of radioactive decay, the convection in the outer core could slow or stop. This would weaken or even cause the collapse of our protective magnetic shield. Losing the magnetic field would have catastrophic consequences. Our atmosphere would be more vulnerable to erosion by the solar wind. Cosmic rays, high-energy particles from deep space would reach the surface in much greater numbers. This increased radiation would be hazardous for any life that might exist. It could lead to higher mutation rates and make the surface environment far more hostile. Our planet, once a vibrant and protected haven, would become exposed and vulnerable to the harshness of space, its surface scoured by unfiltered cosmic energies. Section 7. History Unknowable, the End of Nature's Clocks. One of the most powerful tools we have for understanding Earth's deep past is radiometric dating. This technique relies on the predictable decay of radioactive isotopes. Certain elements like carbon-14, uranium-238, or potassium-40 decay at known rates. By measuring the ratio of the parent radioactive isotope to its stable daughter product in a sample, scientists can calculate how long ago that sample formed. This method has allowed us to determine the age of rocks, fossils, and archaeological artifacts with remarkable accuracy. If radioactive decay stopped, these natural clocks would freeze. The predictable tick-tock of atomic transformation would fall silent. Carbon-14 dating, used for organic materials up to about 50,000 years old, would cease to function. We would lose our ability to precisely date the remains of ancient civilizations or the bones of prehistoric creatures from recent epochs. The story of human history and recent life on Earth would become much harder to piece together with any certainty. The timelines we have carefully constructed would become fixed, with no new entries possible through this method. For older materials, like ancient rocks that tell the story of Earth's formation, we use isotopes with much longer half-lives, such as uranium-lead dating. This technique allows us to peer back billions of years, revealing the age of our planet and the major events in its geological history. If uranium ceased its decay into lead, these clocks too would stop. Our ability to determine the absolute age of the Earth, the Moon, and meteorites would be lost for any future measurements. The vast expanse of deep time would become shrouded in a new kind of uncertainty. Without radiometric dating, our understanding of the history of life would be severely hampered. The fossil record provides glimpses into past ecosystems, but its timeline is anchored by dating the rock layers in which fossils are found. We would lose the ability to correlate fossil discoveries across different continents with precision. The pace of evolution, the timing of mass extinctions, and the emergence of new life forms would become subjects of much greater speculation. The grand narrative of life's journey on Earth would lose many of its most crucial chapter markers, its chronology blurred. Section 8. Technology and healing halted, a world without radioactive tools. Radioactivity, despite its potential dangers, is a cornerstone of many modern technologies and medical practices. Nuclear power plants, for instance, harness the energy released from the controlled fission of radioactive elements like uranium. This process generates a significant portion of the world's electricity, providing a low-carbon energy source. If radioactive decay, and by extension induced fission, which relies on neutron interactions with unstable nuclei, were to stop, these power plants would fall silent. A major source of global energy production would simply vanish overnight. In medicine, radioactive isotopes are indispensable tools. They're used in diagnostic imaging, allowing doctors to see inside the human body without surgery. Techniques like PET scans use short-lived radioactive traces to map organ function and detect diseases like cancer. Radiation therapy, using carefully targeted beams of radiation from decaying isotopes like cobalt-60, is a vital treatment for many types of cancer, destroying malignant cells. If decay stopped, these life-saving diagnostic and therapeutic capabilities would be lost. Medical science would regress, losing some of its most powerful weapons against disease. Beyond energy and medicine, radioactive materials have numerous industrial applications. Smoke detectors, common in homes and buildings, often use a tiny amount of americium-241, whose decay particles ionize air and allow a current to flow. Smoke disrupts this current, triggering the alarm. Radioactive isotopes are used to sterilize medical equipment and food products, killing bacteria and other pathogens. They serve as tracers to detect leaks in pipelines or to study the flow of materials in industrial processes. The cessation of decay would render these diverse and important applications obsolete. Our ability to explore space also benefits from radioactive decay. Radioisotope thermoelectric generators, or RTGs, use the heat from the decay of plutonium-238 to generate electricity for spacecraft venturing into the outer solar system, where sunlight is too faint for solar panels. Missions like Voyager, Cassini, and New Horizons relied on RTGs for power. Without this reliable, long-lasting power source, our exploration of the distant reaches of our solar system would become vastly more challenging, if not impossible for many mission profiles. The lights would go out on our farthest robotic explorers. Section 9. Conclusion. The fundamental role of decay in a dynamic cosmos. Our journey through a universe without radioactive decay reveals a stark truth. This seemingly subtle atomic process is woven into the very fabric of reality. Its absence would create a cosmos fundamentally different from the one we inhabit. The universe would be less dynamic, less diverse, and in many ways less understandable. The quiet, persistent transformation of unstable atoms is not merely a footnote in the laws of physics. It is a critical engine driving change, creating heat and providing tools for both nature and humanity. The silence of no decay would be a profound silence indeed. From the heart of stars, where elements are forged, to the core of our planet, where heat generates geological activity and a protective magnetic field, radioactive decay plays an essential role. It allows us to read the history written in rocks and bones, giving us a timeline for the grand epic of cosmic and biological evolution. It powers our technologies, heals our sick, and enables our exploration of the solar system. To imagine a world without it is to imagine a world with a dimmer past, a colder present, and a more constrained future. It underscores the interconnectedness of all physical laws. The cessation of radioactive decay would lead to a more static Earth, a planet with a cooling interior, stilled tectonic plates, and a weakened magnetic shield exposed to the harshness of space. Our ability to comprehend deep time would be crippled, our historical narratives losing their anchor points. The tools of modern medicine and industry that rely on the unique properties of decaying atoms would become relics of a forgotten science. The universe would still exist, of course, but its character, its vibrancy, and its capacity to evolve would be significantly diminished by this atomic quiescence. Ultimately, contemplating such a scenario deepens our appreciation for the intricate balance of forces that shape our universe. Radioactive decay, often associated with danger, is also a fundamental force of creation and sustained activity. It illustrates how processes at the smallest quantum level can have monumental consequences on the grandest cosmic scales. The constant, subtle hum of atoms transforming is a reminder that we live in a dynamic, evolving cosmos. A universe where even the seemingly eternal rocks beneath our feet are part of an ongoing story, a story largely written by the restless hearts of atoms.